Hello, dear guests. We are starting a new paper representation stage after two special sessions. Because of limited time, I am now starting introducing my first guest from Strathclyde University, Roberto Ravenna. Is a professional marine engineer, tutors through his PhD research in naval architecture. His investigation aims to explore the effects of realistically fold hull surface of hydrodynamic performance of ships. His presentation is about CFD analysis of effect of heterogeneous hull roughness on ship resistance. So the floor is yours, Mr. Ravenna. Here you are.
Thank you. Thank you very much for the great introduction. I will share my screen and my presentation today. Just give me a moment, please. Can you see my screen?
Yes, everything is okay.
Okay, that's perfect. So thank you very much. Well, today I'm going to present a CFD analysis of the effect of heterogeneous hull roughness on ship resistance. I would like to thank my code. I hear that recording is in progress. Okay. I'll start again. So thank you for being here. I'm going to present a CFD analysis of the effect of heterogeneous hull roughness on ship resistance. And I would like to thank for the support all the co-authors from University of Strathclyde and University of Malta. And this study is part of the venture project Horizon 2020. So I will go into the contents of this presentation, which are mainly to give an overview of the roughness effect on ship economy. And then I will move into the aim and objectives, which are related to heterogeneous hull roughness. The methodology, as in the title, is a computational fluid dynamics study. And then I will give all the best of the results we obtained, especially with the definition of a roughness impact factor. Then I will go into the conclusion and recommendation for future studies. Well, hull roughness is something that all naval architects and ship owners are well aware. And it dramatically increases the ship frictional resistance, power, and fuel consumption. And this causes lots of millions lost, and also we concern about environment. So it's something that must not be overlooked. The main causes of hull roughness are biofouling, the failure of fouling control coatings, and corrosions. And it is estimated that with a slime or just a light failure of this fouling control coatings, you can get a fuel increase of 10%, which on one ship could mean 1.8 million a year, and if we scale up to the entire fleet of ship owners, is a lot of money. So we want to address this added resistance. But despite the wide literature available, there is still a limited understanding of the hull roughness effects on ship resistance. Also, the hull surfaces are often treated as uniformly rough, and there is no heterogeneous hull roughness study for any container ship, which are carrying most of the goods nowadays around the world. So eventually there is limited support for ship owners in hull maintenance decisions. Therefore, the present study aims to address fill these gaps, and conducting a heterogeneous hull roughness scenarios investigation on the benchmark KCS hull. And this way it could be possible to investigate more how the flow affects, how roughness affects the flow regime. And eventually the main aim, the final aim would be to give some extra tool for ship owners to decide on targeted strategies for hull maintenance. Just jump into the methodology. So there is a solid literature within the turbulent boundary layer theory, which has been developed to assess the effect of increased roughness on ship performances. Recent studies demonstrated that CFD can accurately predict this effect on ship resistance, provided that the roughness function model, delta U plus, are known, and these are characteristic of each surface. In this study, the roughness function model was developed and validated from a previous study of one of the co-authors, and it was developed from towing tank experiments on a flat plate with a specific sun grain roughness, which tried to mimic a light rough scenario. Then methodology is still another slide to elaborate on what are the simulations that we conducted. So once we implemented in a modified wall function approach this roughness function model, we decided on different scenarios with different coverage, which in this case, can you see mine? Yeah, I think so. So different scenarios, and as you can see, we will describe them and also compare with the full smooth and full rough cases. And the simulations were all conducted in star CCM on the benchmark cruiser container ship in model scale. Of course, the findings will try to help the ship owners in the decision making. Well, some preliminary results here. I wanted to show some graphics behind the data that I will show later. So as you can see, the figures, and we know that the wall shear stress, when the wall shear stress increases, the local skin friction coefficients and the roughness Reynolds number will be affected. And in this case, I try to highlight this effect of the increase of wall shear stress. And it is also known that in the fore part of the hull of ships, there is a more significant impact on the of the wall shear stress on the skin friction and roughness Reynolds number. And this is due to the active transition between the flow and the fore part of the hull. So accordingly, again, in this slide we can see that the bulbous bow is quite could be observed that it's quite red, and it means that the skin friction there is really high, while on the aft regions there is very little of these characteristics, confirming that the fore part are more influencing the roughness, the ship resistance. Maybe this figure could clarify more what I wanted to show you. And the boundary layer characteristics are here presented, and we can see that, of course, if in the case of full rough conditions, we have a thicker boundary layer, while on smooth conditions, like ideal conditions, this is the boundary layer characteristics. These are the boundary layer characteristics. And the interesting thing is that the bulbous bow, just the bulbous bow rough, gives a boundary layer characteristic which is more similar to the full rough case than of the full smooth case. While, for example, more extensive areas such as the midship even if they're rough, they influence the boundary layer less than such a small part as the bulbous bow. Well, the diagram in this slide tries to quantify this effect. So I'm showing the resistance coefficients obtained from the simulations and compared with the full rough case. And of course, the full rough case gives us the biggest added resistance, the greatest added resistance. But the small bulbous bow, compared with the bigger stern condition, can be already noticed that there is a more added resistance due to that little area of the bulbous bow than of the stern. This confirming and making things more interesting. And I will show in the following slide how we decided to take this into account. So to describe this non-proportional impact of the different heterogeneous roughness scenarios, we introduced a roughness impact factor, which has been defined as in this equation where this delta CFI and the VUCS rough I are characteristics of the configuration in exam. And on the other side, we have the general conditions, so the full rough and the total wetted surface area. And it can be seen that the roughness impact factor of the bulbous bow is way bigger than the rest of them, despite being the smallest area. And so, on the other hand, as I mentioned before, the stern has the least impact on the ship resistance characteristics. This gives an idea of where we could start looking into when we would like to clean this hull. And of course, due to the way it's been defined, this roughness impact factor, we have that for the full rough conditions, it is unitary, evidently. And so the diagram highlights these characteristics. And that's all I wanted to show. I'm sure you'll have probably questions. So these are the conclusions. I showed you quickly the roughness effect on shipping economy, the scope of this study, and the strategy, which has been at the moment CFD based, but probably for future study it could be also compared with experimental studies. And also these simulations were conducted in model scale, but at the minute we are working on full-scale simulations as well, and also thinking of further roughness scenarios, which can still be all discussed and addressed with the so defined roughness impact factor. So this is me, and I hope you enjoyed the presentation, and thank you for your attention. I left a couple of minutes, so maybe we can discuss or have all the questions you may have. So please.
Thank you. Thank you, Mr. Ravenna, to you and your colleagues for contribution to our Congress. And I have to pass the next one. So thank you again. Have a good day.
Thank you. Thank you. It was an honor to participate in this conference. Really enjoyed. And yeah, I'm looking forward to see further developments of it. And yeah, it was good to meet you, everyone. Thank you.
Nice to meet you too. Thank you.
Thank you.